The terminal hasn't changed in 40 years. You type a command, the system runs it, you're done. It's a straight line from what you want to what happens. That's the contract we've all lived with. Type something, get a result. But something fundamental shifted between 2024 and 2025. It isn't about what the terminal can do technically. It's about what it's becoming. The terminal is no longer just a command dispatcher. It's turning into an orchestration layer, a policy shell, a place where AI agents plan, execute, and adapt in real time. This isn't about faster autocomplete or better suggestions in your editor. This is about reframing how software gets built and reviewed from the ground up, because the teams that still treat the terminal as just where you type commands are about to get left behind. The structural flaw in how we build software. For decades, the developer workflow was predictable. You wrote code, someone reviewed it, you deployed it. Each step was human-driven. Each step was a decision point. You moved through them one by one. Then AI arrived in the editor. We got Copilot chat and inline suggestions that actually understand context. Productivity went up and developers started shipping features faster because the editor finally got smarter. But here's the structural flaw that nobody talks about. We're still treating AI like a tool, not a system. A tool just responds to your input. You ask a question, it gives an answer, and then you decide what to do next. You stay in control. You make the calls. That works for autocomplete, but it breaks everywhere else. The real bottlenecks aren't hiding in the editor. They're in the terminal. They're in the CI pipeline and the code review queue that's 3 weeks deep. They're in the modernization graveyard where legacy code stays legacy forever. These are the places where intent meets execution. This is where a good idea becomes a broken deploy or a refactor introduces coupling that nobody saw coming. Technical debt piles up quietly in these corners until the entire code base becomes impossible to maintain. The structural mistake we made was optimizing the thinking layer while ignoring the execution layer. We made the editor smarter and improved how developers write code, which definitely matters, but we left everything else exactly as it was. The terminal is still just a command dispatcher. The pipeline is still just a sequence of scripts. The review process is still just humans reading code line by line, hoping they catch issues before they hit production. Modernization is still a manual ordeal that takes months because someone has to figure out the old system and hope they don't break it. The orchestration layer never got smart. We optimized for thinking. We ignored execution. And this is the shift. The shift from tools to agents. There is a category difference between a tool and an agent. The tool responds to your input. You ask it something, it gives you an answer. And then you decide what happens next. You stay in the loop, you keep control. An agent is different. An agent has a goal. Within the constraints you set, it pursues that goal. It makes decisions, it takes actions, it observes the results, and then it adapts. You don't direct every step, you set the policy. And the agent operates within it. That is the shift happening right now. Copilot CLI is an agent. You describe a task in natural language like asking it to add pagination to an API endpoint or refactor a controller for clarity. That isn't a question. It's an intent statement. The agent reads it and understands the code base. It sees the structure, the patterns, and the dependencies. It plans the steps and executes them in sequence. If a test fails, it doesn't stop and ask you what to do. It analyzes the failure to understand why the test broke, modifies the implementation, and tries again. When the work is finished, it reports back on what it built and what changed. That isn't a tool assisting you. That is an agent completing work. Copilot Code Review is an agent. It isn't just flagging syntax errors or running a linter. Those are tools. The agent reads a PR and understands the architecture. It knows where the boundaries are and sees when code crosses into another layer. It reasons about coupling and checks against solid principles. It looks at multiple files instead of seeing one change in isolation. It catches the architectural problems that a human reviewer would miss because they are tired, and this is the 10th PR they have read today. A tool flags problems, an agent understands context and prevents them. Modernization agents work the same way. Legacy code is often buried in business logic that spans dozens of functions across multiple files. A tool would find old patterns and suggest replacements. An agent does something different. It reads the entire system and builds a map of what does what. It extracts the business logic and identifies the invariants that must never change. Then it re-implements that logic in a modern stack. It uses modern code and modern patterns while preserving every behavior and every contract the system made to the outside world. That isn't find and replace. That is deep understanding followed by transformation. So what's actually happening when you shift from tools to agents? With a tool, you stay in the loop. You make the decisions. The tool assists. You write code and the tool suggests the next line. You review the suggestion and you accept or reject it. You are constantly deciding and constantly guiding. With an agent, the agent stays in the loop. It makes decisions within your policy. You don't direct every step. You set the constraints and define what success looks like. You say what patterns to follow and what rules to obey. Then the agent operates. It makes thousands of micro decisions about dependencies, variable names, and function structures. It doesn't ask you about every single choice because it operates within the policy you set. You supervise, you don't direct. That isn't a small difference. It's a reorganization of how software gets built. When you have 100 developers and one code review tool, the tool helps a little. But when an agent reviews every PR before a human ever sees it, the quality bar for the entire organization changes. It enforces architecture constantly. It prevents mistakes before they happen. It raises the baseline. It isn't just assisting, it is actively shaping how work flows through the system. And the terminal is where this reorganization is most visible, because the terminal is where the real work happens. Why the terminal became the center of gravity. The terminal is where developers already live, not where they visit, where they live every single day. In Git commands, in CI/CD debugging when a build fails at 3 a.m., in infrastructure management and log analysis, the editor is where you think. You are composing and drafting ideas. But the terminal is execution. It's where thought becomes action. But here's the problem. For years, we only optimized the thinking layer. We built better autocomplete and smarter code completion. We made the editor intelligent because that is where ideas form. We assumed that faster thinking meant faster writing. But we ignored the execution layer. The terminal stayed the same. It was just a command dispatcher. You had the knowledge about what to run, you typed it, and it ran. If something broke, you read the error and figured it out yourself. The terminal didn't get smarter, it just got faster. That imbalance is what we are about to fix. With agentic shells, the terminal has become intelligent. It isn't just a dispatcher anymore. It understands intent. You don't describe the exact command, you describe the goal. You tell it to deploy a feature to staging and validate the integration tests. The agentic shell understands that intent. It plans the workflow and figures out which commands need to run in what order. It executes them and watches for failures. If something breaks, it analyzes the error to understand what went wrong. It modifies the approach and it tries again. The terminal has moved from execute what I tell you to accomplish what I want. This is where the real leverage lives. It isn't in suggesting the next line of code. That is just optimization at the edges. The real leverage is automating the entire workflow that takes code from written to validated. The whole pipeline, the whole orchestration. This sequence used to require human knowledge and human trial and error. Now, a developer can describe a complex task and the agentic shell breaks it into steps. It runs tests and checks results. It modifies code if those tests fail. It validates security and checks performance. It handles all the machinery that used to require someone to understand every tool and every edge case. That isn't a productivity improvement. That is a structural reorganization of how work flows. The teams that understand this first will move faster. Not incrementally, dramatically, because they aren't optimizing the edges of the developer experience anymore. They are automating the core machinery of software delivery. The terminal is no longer where you type. It's where the work happens. The teams that don't realize this yet will keep treating the terminal like a legacy tool, a command dispatcher, something you use to run things you already know how to run. But in reality, it does the opposite. Let's look at what this actually looks like. The Agentic Developer Stack, a new model. The Agentic Developer Stack isn't just a new tool or a single system. It's a model built on 4 distinct layers. They operate independently, but they're wired together. Each layer is autonomous, each one is intelligent, each one has a specific job, and they communicate through structured handoffs. The first layer is Orchestration, which is Copilot CLI. This is where you sit and describe your intent in natural language. You aren't writing scripts or memorizing commands anymore. You're saying what you want to accomplish, like adding pagination to an API endpoint or refactoring a controller for clarity. The CLI agent reads that request and looks at your code base to understand the structure and existing patterns. It plans the workflow by breaking the task into steps, figuring out which files to change and what the success criteria look like. Then it executes those steps in the terminal one by one. If a test fails, it adapts. It modifies the code and tries again without asking for permission on every microdecision. It operates within the policy you've set, converting your intent into a workflow that actually runs. The second layer is transformation, the modernization agent. Legacy code goes in, modern code comes out. The agent reads the old system and builds a complete map of how data flows and where the hidden dependencies live. Once it understands the system semantically, it extracts the actual business logic. Then it re-implements that logic in a modern stack with modern frameworks. But everything the system promised to do, it still does. Every edge case and every contract remains intact. This layer isn't just about replacing old patterns, it's about rebuilding the system to do the same thing better. The third layer is validation, the code review agent. Every change gets reviewed, but not by humans. The agent reads the code and understands the architecture, seeing exactly where a change crosses an architectural line. It verifies solid principles and looks for ripple effects across multiple files. It catches the issues a human would miss because they're tired or switching contexts. It doesn't just flag problems, it enforces your architectural policy. This layer ensures that every change actually fits the system it's going into. The fourth layer is execution, the coding agent running in the cloud. Some tasks need a full environment for cloning repos, installing dependencies, and running security scans. This agent operates in a managed, ephemeral environment in the cloud. It has everything it needs to run real tests against the real codebase. It opens pull requests, documents the work, and waits for feedback. This layer manages execution where nothing can accidentally break production. Each layer is autonomous, but they work as a feedback mesh. Validation can send work back to transformation if it sees an architectural violation. Execution can surface issues back to orchestration that weren't anticipated. The human sits above all of this. You set the policy, you define the guardrails, and you make the final decisions. You aren't out of the loop. You're just in a different position. This is the structural shift. AI manages the workflow, and you manage the policy. The orchestration layer, Copilot CLI and agentic shells. Copilot CLI is fundamentally different from a code autocompleter. It isn't predicting your next line or suggesting syntax. It's a workflow engine embedded in your terminal. You aren't interacting with a tool. You're delegating to an agent. The difference starts with how you communicate. You don't describe commands. You describe intent. When you tell it to add pagination and update the tests, you're stating a goal. The agent figures out how to get there. The CLI agent reads your codebase to map the modules and identify your coding conventions. It understands the standards you've documented. Then it plans. It breaks the task into specific steps, deciding which files need to change and in what order. Once the plan is solid, it executes. And here is what happens when something breaks. In a normal environment, you would read the error and modify the code yourself. The agent does exactly that. It analyzes the failure to understand what caused it, then it modifies the implementation and runs the test again. It doesn't ask you before each iteration. It operates within the constraints you've set until the tests pass. This is agentic behavior. You aren't telling it to execute a command, you're telling it to achieve a goal. The agent operates within a policy envelope. Its freedom is bounded by the rules you define. You decide which files are off limits and which quality gates it needs to clear. The agent incorporates these constraints into its reasoning from the start. It doesn't fight the rules, it uses them to find the right approach. Latency is critical here. If an agent takes 30 seconds to respond, developers won't use it. You need feedback in seconds, not minutes. Copilot CLI has been optimized for speed, with updates showing a 75% improvement in response time. This comes from architectural shifts like prompt caching and streaming output. It uses context compression to send only the relevant code and parallel execution to run multiple checks at once. The agent needs to feel responsive, like it's working at your pace. Context is the other half of the equation. The agent needs to understand your project deeply, including the gotchas that aren't written down. This is why project memory matters. Files like architecture.md or a domain glossary are foundational. The agent reads these before every task to ensure continuity. Without this context, the agent generates code that is technically correct but doesn't fit. It might pass the tests, but it violates your patterns. With context, the code actually belongs in your codebase. It respects the decisions you've made about how things should be structured. But the orchestration layer only handles one part of the workflow. The transformation layer, modernization agents. The orchestration layer decides what needs to happen. The transformation layer is what actually happens. And this layer solves a problem that most organizations have basically given up on. Legacy code. Modernization agents exist for one specific job. They take old code and make it new without breaking it. That sounds simple. It isn't. In reality, it's exponentially harder than writing new code from scratch. Because modernization isn't just find and replace. You can't just swap out old syntax for new syntax and call it a day. Old code carries hidden logic, business rules buried in conditional statements, data constraints that nobody ever documented, edge cases handled in ways that make no sense until you understand why they exist. The code didn't start as garbage. It evolved. It handled problems that emerged over years of production. It solved bugs that happened in the middle of the night. Every weird pattern exists because something broke and someone fixed it. A modernization agent has to excavate all of that before it can touch a single line. The first thing it does is what you'd call code archaeology. The agent reads the entire legacy system, not in summary form, not as an overview. It builds a complete map. It identifies entry points. Where does data come in? Where do requests start? It traces data flows. Where does information move? How does it transform? It finds hidden coupling, places where modules that shouldn't know about each other actually depend on each other. It identifies the business logic, the thing the system actually does, beneath all the layers of framework and historical decisions, once it understands the system. And this understanding runs deep. It generates documentation. What does this module do? What are the key workflows? What are the assumptions it makes? What are the gotchas, the things that will break if you change them without understanding why they exist? This documentation becomes project memory. It gets fed back into the agent on every iteration. The agent doesn't lose context, it builds on what it learned. Then the agent works, not in one massive refactor. In small reversible slices, one module at a time, one service at a time. Each slice is tested. Does it still do what it did before? Each slice is reviewed. Does it fit the architecture? Only after validation does it move to the next slice. The critical insight here is what modernization agents don't do. They don't replace human architects. They don't eliminate the need for human judgment about what the system should become. What they do is handle the mechanical work, code generation, dependency updates, test generation, boilerplate. The stuff that's necessary but not interesting. Humans handle architectural decisions. Humans decide what patterns to follow in the new system. Humans own the strategy. The agent owns the execution. On Saddle Bench Pro. a benchmark of real software engineering tasks taken from actual GitHub repositories. Modernization agents paired with review agents showed something interesting. Claude Sonnet, paired with a GPT-based reviewer, closed 74.7% of the performance gap between Sonnet and Opus. That's the expensive model. That means a mid-tier model, when paired with strong validation, can approach top-tier performance. The implication matters. You don't need the most expensive model if you have a good review process. But here's what separates successful modernization from failure: context. The agent needs to read your architecture docs, your domain glossaries, your test strategies, the gotchas file that lists all the weird things that will bite you if you're not careful. Without context, the agent generates code that's modern in syntax but ancient in structure. It's technical debt wearing new clothes. With context, it generates code that preserves behavior while modernizing the implementation. That's the difference between a modernization project that ships and one that becomes another graveyard of abandoned work. But code transformation only matters if the output gets validated. The validation layer: code review, agents, and architectural enforcement. The problem with code review is deceptively simple. It doesn't scale with the velocity of code generation. When you have one developer writing code and one reviewer checking it, the system works, they trade off. Writer finishes a PR, reviewer reads it. Feedback happens, changes get made, it merges. When you introduce an agentic system that can generate more code in a day than a human reviewer can reasonably read in a week, that model collapses, the queue grows, the feedback gets slower, the review becomes a bottleneck, and bottlenecks are where quality deteriorates because people start rushing. Code review agents exist to solve this, but not in the way you might think. They don't replace human review. They filter it, they handle the first pass, the mechanical checks, the obvious issues. This clears the queue so humans can focus on what humans are actually good at: reasoning about architectural fit, understanding business intent, making judgment calls about trade-offs. What gets checked at this layer matters. A good code review agent looks at security, input validation, authentication boundaries, data exposure, known dependency vulnerabilities. It checks architecture, layer violations, boundary crossings, coupling that shouldn't exist, solid principles. It checks testing, coverage gaps, missing edge cases, weak assertions, test quality. It checks performance, N+1 queries, inefficient loops, memory leaks, resource exhaustion patterns. It checks style, naming clarity, consistency with local conventions, readability. But here's where most code review systems fail. They look at these things in isolation, one file at a time. The agent we're talking about here understands architecture. It reads a PR and it knows the boundaries in your system. It sees where the change crosses an architectural line. It knows what patterns you've established. It can reason about multi-file impact. It catches the architectural problem that would break the system in unexpected ways, the one that wouldn't show up until production traffic hit it. This requires context, not just your code, not just the change being reviewed, rules files that document your architectural constraints, pattern documents that show how things should be structured, structural trees that illustrate the component hierarchy. Without these, the agent is a linter on steroids, useful but shallow. With these, it becomes an architectural enforcer, actively shaping the quality of what gets merged. GitHub's Copilot code review now runs on a fundamentally different architecture than traditional review systems. It's not one model reading a PR. It's multiple specialized agents cooperating. A style agent, a security agent, an architecture agent, a testing agent. Each one runs independently. Each one produces findings. An orchestrator aggregates them, deduplicates redundant findings, resolves conflicts, produces a unified review that's actually coherent instead of a mess of contradictory suggestions. The benefit of this multi-agent approach is that you get multiple perspectives on the same code. Different agents catch different things. A security-focused agent might miss a performance problem that a performance-focused agent would flag. But together, they see more than any single agent would. Cross-model review adds another layer to this. One model family generates the code. A different model family reviews it. Claude reviewing GPT-generated code. GPT reviewing Claude-generated code. Different model families have different failure modes. What one model family reliably catches, another might miss. By bringing different architectures and different training to the review process, you reduce correlated failures. You catch more actual problems on complex, multi-file tasks, the ones where ripple effects matter, where architectural decisions show up as subtle breakage. Cross-model review improves outcomes by 3.8 to 4.8 percentage points. That's on top of baseline performance. That's real improvement on the kinds of changes that matter most. The structural shift here is the one that makes the entire system work. Validation moves from being a human judgment process to being an automated enforcement process with human oversight. The agent enforces the policy, the rules get checked, the patterns get validated. The human reviews the output of that enforcement and makes final decisions on edge cases where judgment is needed. This is why the validation layer isn't optional. It's what keeps the transformation and execution layers from generating garbage at scale. The execution layer, coding agents and cloud environments. Coding agents operate completely differently from Copilot CLI. That difference is fundamental. Copilot CLI is synchronous. It's local, you're in the terminal, describing a task. Watching the work happen, you get feedback in seconds because the agent has access to your local machine, your tests, your tools, your dependencies. Coding agents are asynchronous. They're remote. You create a GitHub issue, assign it to Copilot, and then you walk away. The agent takes over in a managed environment. You get feedback when the work is finished, not while it's happening. The environment is ephemeral. It exists for the duration of the task, and then it's gone. This distinction changes what's possible. Copilot CLI is for incremental work, quick refactors, small features, tasks that finish in minutes. Coding agents handle the complex stuff, full feature implementation, major refactors, tasks that need the entire repository, all dependencies, the full test suite, and the real CI/CD pipeline. When you assign a task to a coding agent, it starts by setting up its space. It clones your repository. It installs every dependency, not just the ones on your local machine. It reads the codebase, maps the structure, and identifies the architecture. Then it plans the implementation. When it writes code, it isn't working in isolation. It works against a real repository. It runs the actual tests that would run in production, not simplified versions. If a test fails, the agent analyzes the failure and adapts. It modifies the code and runs the tests again. This iteration happens without asking for permission because the agent is pursuing the goal you set. It works within your constraints, but it doesn't interrupt you for every minor failure. When the work is done, the agent doesn't just hand you a file. It runs security scans. It checks test coverage. It validates against your quality gates. Only after it confirms the requirements are met does it open a pull request with a detailed description, with test results, with a summary of what changed and why. The pull request is the output that matters. It's the artifact. You review it, you leave comments, you request changes. The agent reads that feedback and understands your corrections. It incorporates them and pushes new commits. This is a feedback loop. It isn't generate once and accept. It's agent generates, you guide, agent refines. The environment is the enabler. The agent isn't guessing if the code works. It has everything. Real code, real dependencies, real security scanning. When the agent claims something works, it actually works because it's been tested against your actual system. The environment is also safe. The agent can't accidentally break production. It can't merge to main. It can't deploy without approval. Everything it generates appears as a pull request for you to review. The constraints are intentional. The agent can only change the repository you specified. It can't touch multiple repos in one run. It opens exactly one pull request per task. These aren't limitations, they're design choices. They force focus, they make the output reviewable, they prevent runaway behavior, where an agent makes cascading changes across your entire system. On real code bases, these agents have shortened cycle times. Technical debt has actually decreased because the agent works within the constraints you set, and the review process enforces them. The structural shift is clear. Execution moves from you write code locally and push when ready to the agent executes the full workflow in a controlled space while you review the output. But these layers only work if they're connected. How the layers connect the orchestration problem. The 4 layers exist independently, but that's only useful if they're actually talking to each other. This is where most teams fail. They deploy the agents, they optimize each layer separately, but they never wire them together. The orchestration layer plans something. The transformation layer generates something different. The validation layer rejects it, and nobody knows why. The system becomes a mess of disconnected agents producing conflicting outputs. This is the orchestration problem. How do you connect agentic systems so they reinforce each other instead of creating bottlenecks? The answer is structured handoffs, not loose communication. Not, hey agent, go do a thing, but a structured exchange of information with clear expectations. Here's what a real workflow looks like. A developer opens Copilot CLI to plan a refactor that touches multiple files. They describe the goal. The CLI agent plans the workflow, breaks it into steps, and identifies which files need to change. The plan isn't vague. It's a specific document that another system can read and understand. The developer reviews the plan. When they approve it, the plan moves to the modernization agent. Not as a suggestion, but as a specification. The transformation layer reads the plan and executes it. It implements the refactor, writes the code, and runs tests locally. If tests fail, it adapts and refines the approach based on what it learned. When the refactor is finished, the output moves to code review. Again, this is structured. The validation layer reads the change and checks for architecture violations. It looks for security issues and test coverage gaps. If validation passes, the PR is ready. If it fails, feedback goes back. Not to the developer, but to the transformation layer. The agent reads the feedback, understands what didn't work, and modifies the implementation. The coding agent handles the environment. It manages the branch. It runs the full test suite. It opens the PR with documentation and waits for human feedback. The loop continues. The human leaves comments, the agent reads them, and the agent pushes new commits. This isn't linear. It's a mesh. Each layer can communicate with every other layer. The execution layer can tell orchestration that it found an edge case the plan didn't anticipate. Orchestration can then trigger a new workflow to handle it. The validation layer can tell transformation that a specific pattern doesn't work in this architecture. Transformation adapts. The human sits above this entire system. You aren't out of the loop. You're in a different position in the loop. You set policy, you define guardrails, you handle the exceptions where judgment is needed. The agents handle the mechanical work. What makes this possible is clarity. Each layer has a defined interface. Orchestration outputs a plan. Transformation accepts that plan and outputs code. Validation accepts code and outputs a review. Because the interfaces are clean, layers can be swapped. You could replace the transformation layer with a different agent. And as long as the input format is the same, it works. The system is composable. But none of this works without continuous data flow. Each layer needs context from the previous ones. The validation layer needs to know what the transformation layer was trying to accomplish. The execution layer needs to know what orchestration decided about priority. Without that, the agents are working in isolation. This is why project memory is foundational. Architecture.md, gotchas.md, teststrategy.md. These files are read by every agent to provide continuity. They ensure that each layer understands the context from all the others. Without shared context, each layer is isolated. It makes local decisions. Good output from layer 1 becomes bad output from layer 2 because they aren't talking. With shared context, they work as a system. Each layer builds on what the previous layer learned. The context problem. Why most modernization agents fail. Most organizations follow a predictable pattern when they deploy a modernization agent. They point the tool at a mountain of old code. They expect magic. The command is simple. Here is the legacy system. Make it modern, then they wait. At first, it looks like it's working. The agent runs, it scans the code, it generates an output that actually compiles. The tests pass, the team celebrates. But then, reality hits. The code is technically correct, but it doesn't actually fit. The syntax is modern, the framework is new, but the architecture is a mess. It violates the patterns your system relies on. It introduces hidden coupling. It completely misses the business logic. What you've actually built is modern technical debt. It's the old broken system, just wearing a new set of clothes. Most teams fail at modernization for one specific reason. The agent didn't have context. Think of it like asking a contractor to renovate your house. But you don't give them the floor plan. You don't show them the building codes. You don't even give them a budget. The contractor can work, they can swap out parts, but they don't know what they're building toward. They don't understand the constraints. They don't know what actually matters to the structure. The agent is operating blind. Context engineering is the shift that separates success from total failure. Most teams skip this work. They assume the agent is supposed to figure it out on its own. It doesn't. You have to start with code archaeology. Force the agent to analyze the legacy system before it touches a single line. It needs to see the hidden dependencies. It needs to find the entry points where data flows in. It has to map the coupling between modules that should have stayed separate. The agent needs to find the business logic buried deep inside messy conditionals. It needs to see the gotchas that will break the system if they're changed. Once the agent truly understands the system, it generates documentation. Not generic summaries, specific structural documents. What does this module actually do? What are the key workflows? What assumptions is the system making? What will break the moment you touch it? These files become the project memory. Architecture.md, domaiнгlossary.md, gotchas.md. You keep these in your repository. They aren't static. They evolve as the project moves. But here's the problem. Most people think context is a one-time task. In reality, it's iterative. When the agent finishes a task, you don't just merge and move on. You update the memory files with everything you just learned. You add the new gotchas. You refine the glossary. The next time the agent runs, it has more context. It has a better understanding. It generates better code. This feedback loop is what keeps your project out of the graveyard of failed modernization attempts. The research is clear on this. Teams that maintain a living project memory see 30 to 60% better outcomes. That isn't a small tweak. That is the difference between shipping a product and watching a project die. The structural insight is this. Modernization isn't about the agent, it's about the context you give it. This is why context engineering is becoming its own discipline. Senior engineers are now designing how agents consume information. They create pattern files to show how components should look. They write rule files that encode the architectural constraints. These aren't just technical rules, they are business rules, data constraints, integration patterns. The agent uses these files as a constant reference. It doesn't just make code, it makes code that actually fits your specific system. Does this take more work upfront? Yes, you're building structures that wouldn't exist otherwise, but the payoff is massive. The agent generates better code. Better code needs less review. Less review means less rework. And that is how a modernization project actually finishes, instead of stalling out halfway through. But even with perfect context, agents make mistakes, and that's where validation becomes critical. The rubber duck protocol, cross-model review. Most organizations expect the best results to come from the biggest models, but in reality, a mid-tier model with strong validation beats a top-tier model working alone. GitHub's internal research proved this. Claude Sonnet 3.5 is faster and cheaper than Claude Opus, but it's also less capable when things get difficult. That's the trade-off. You get speed, but you lose some depth until you pair it with a reviewer from a different model family. When they paired Claude Sonnet with GPT-4 as a reviewer, something happened. It closed nearly 75% of the performance gap between Sonnet and Opus. That's a massive shift. It means you get top-tier results without paying top-tier prices. But this only works because the reviewer comes from a different family. If you have Claude Sonnet write a plan and then ask Claude Sonnet to review it, you won't see much change. The model is just thinking the same way twice. It will repeat its own blind spots. It will miss the same things it missed the first time. Different model families have different training. They have different architectures. They have different ways of failing. What Claude misses, GPT might catch instantly. What GPT overlooks, Claude will flag. When you combine them, the gaps disappear. This is the foundation of the rubber duck protocol. One model generates, a different model family reviews. The reviewer's job isn't to say looks good. Its job is to challenge the plan, to find the blind spots, to catch what the first model missed. Inside the Copilot CLI, it looks like this. You describe a task. The primary agent, maybe a Claude model, reads your intent. It looks at your code. It builds a plan. But before it executes, that plan goes to the rubber duck. The rubber duck is a different model, usually GPT. It reads the plan and looks for gaps in the reasoning. It looks for unjustified assumptions. It finds the edge cases that weren't considered. When a task touches 5 different modules with complex dependencies, that's when the review matters. A simple change might be fine on its own, but a complex refactor is where the rubber duck earns its keep. It finds the architectural flaw the primary agent ignored. It identifies the edge case that would have crashed in production. It catches the pattern violation before it creates more technical debt. The timing here is important. The reviewer doesn't block the work. The primary agent starts implementing while the rubber duck is still thinking. It's asynchronous. When the review comes back, the agent incorporates that feedback. It refines the plan. It updates the code. It isn't stop and wait. It's work in parallel and improve as you go. The results are measurable. On complex, multi-file tasks, this cross-model review improved outcomes by nearly 5 percentage points. That is a consistent improvement across almost every type of problem. But the real takeaway isn't about raw power. It's about collaboration. It's about using the differences between models as a feature. The structural shift is subtle. Validation is no longer a single judgment. It becomes a conversation between 2 different ways of thinking. The primary agent proposes, the reviewer challenges, the agent refines. This is the opposite of the bigger is better mindset. It's the collaboration is better model. It changes what you need to buy. You don't need the most expensive model for every single task. You need a capable model paired with a smart reviewer. The cost goes down, but the results stay high. It changes how you think about validation. It isn't a gate at the end of the road. It's a participant in the process. The reviewer shapes the output while it's being made, not after it's already finished. But none of this works if the agents can't actually understand the code they're supposed to be reviewing. Building the agent's mental model, code-based understanding. An agent's decisions are only as good as its understanding of the work. I'm not talking about syntax. Any parser can read code. I'm talking about semantic understanding, architectural understanding, and the why behind the shape of your system. A codebase isn't just a collection of files. It's a series of patterns that evolved over years. It's conventions that nobody ever bothered to write down. It's decisions made under pressure during a midnight outage that never got documented. It's the history and the context of 1,000 small choices that make your system unique instead of a generic app. The agent needs to absorb all of that before it ever touches a line of code. It starts with the module structure and how things actually depend on each other. You don't just need a file list, you need the real dependency graph. The agent has to know what calls what, and more importantly, what is forbidden from calling what. It needs to see the architectural boundaries where the API layer ends and the business logic begins. It has to understand which lines can be crossed and which ones are hard walls. Then there are the coding patterns, not what the language manual says, but what your team actually does. How you name variables, how you structure your classes, and how you organize your functions. The agent needs the history of your choices. It needs to know why you chose this specific framework or why you split the system this way 3 years ago. It needs to see the constraints, the weird edge cases, and the landmines that will explode if they're touched. This is where context engineering becomes the foundation of the work. You don't just hand an agent a repo and hope for the best. You deliberately build structures that teach the agent how the system lives. Architecture decision records, or ADRs, are the first tool for this. They don't just record a decision. They record the problem, the alternatives, and the trade-offs. When the agent reads these, it finally understands the reasoning behind your architecture. Pattern files are the second tool. These show the right way to solve a problem in your specific codebase. It's an example of how you structure a service or handle data validation. The agent studies these and uses them as the template for everything it builds next. Structural trees show how components are organized. Not as a long essay, but as a clear hierarchy. The agent uses these trees to make sure its own output actually fits into the world you've defined. Context windows are the final lever. When the agent starts a task, you don't dump the whole codebase into its lap. You give it the surrounding code, the interacting modules, and the specific rules for that area. This is the principle of context over coverage. A deep understanding of what matters right now always beats a shallow understanding of everything. The agent's mental model builds through these layers. Each one adds a new level of clarity until the agent has a coherent picture of the system. This process starts with code archaeology. Before the agent transforms anything, it analyzes the system and builds its model. It generates documentation that becomes the project's memory. Over time, that memory gets refined and sharpened. The quality of what the agent produces is directly tied to the quality of this mental model. A strong model produces great code, but a weak model produces code that's technically correct while being architecturally broken. This isn't a one-and-done task. As your system grows, new patterns and constraints will emerge. The documentation has to grow with it. ADRs need updates when decisions change, and pattern files need a refresh when your standards evolve. Treat context as a living artifact. Don't build it once and forget it. You have to maintain it because it's the only thing determining the quality of what your agents can actually do. Safety and guardrails, bounded autonomy. There's a tension we have to resolve before agents can work at scale. You want them to be smart enough to make real decisions, but you can't have them being so autonomous that they wreck production while you're grabbing coffee. This is the problem of bounded autonomy, providing freedom within a set of constraints. The solution is a system of layered guardrails. These have to be so fundamental to the environment that the agent doesn't even think about bypassing them. It starts with permissioned guardrails. The agent can touch specific files or modify certain services, but it can't delete a database without a human saying yes. You define the perimeter and the agent stays inside. It doesn't stay there because it's being forced. It stays there because it understands that's how the system works. It reads the policy, builds it into the plan, and accounts for those limits before it ever generates code. Policy guardrails are the next layer. These are the laws of your organization. No hard-coded secrets, no direct database access from the front end, no circular dependencies. These aren't just suggestions, they are hard rules the agent has to follow. It treats these policies as the primary constraints on its work. Validation guardrails are the third layer. The agent's work has to pass through specific gates. The tests have to pass, the linters have to be clean, and the security scans have to be green. The agent knows these checks are coming. It builds toward passing them, and if it fails a check, it goes back and adapts. Review guardrails are the final safety net. The agent's output never goes straight to production. It goes to a human first. High-risk changes always need an explicit sign-off, while lower-risk tasks might be auto-approved if they clear every validation gate. The human stays in the loop because that's how the workflow is designed. Here's the most important thing about guardrails. They aren't restrictions. They are the structure that makes it safe for the agent to move fast. They aren't the friction, they are the rails. The agent doesn't fight against these boundaries. It uses them to reason. When it plans a task, it's already calculating which files it can touch and which policies it needs to respect. It isn't trying to see how much it can get away with. It's trying to hit the goal within the lines you drew. Sandboxing is what makes this work in the real world. The agent never works in your actual production environment. It works in ephemeral spaces that exist only for the duration of the task. It clones the repo, installs the dependencies, and runs the tests in total isolation. Nothing it does can touch your live system. Every change is proposed as a pull request and validated in CI/CD before it ever gets merged. This is actually safer than traditional local development. You can't accidentally push to the wrong branch or deploy a change before the tests finish. The agent works in the sandbox, the outputs are just proposals, and the validation is automatic. The human is always the one in control. You set the guardrails, you define the permissions, and you set the gates. You make the final call on what gets approved. The agent executes the policy. It doesn't create it. This is the structural shift that makes autonomous agents a reality. Safety doesn't come from a human watching every single move the agent makes. Safety comes from a policy that prevents the bad things from happening in the first place. It scales because the policy handles the routine work, leaving the human to focus on judgment calls and edge cases. The agent's ability to respect these guardrails is exactly what allows it to scale. Without them, you'd never let an agent near your codebase. With them, you can let it work across the entire system because you know the policy is there to catch what matters. But even with the best guardrails in place, failures still happen. Handling failure, agent self-healing and iteration. When an agent fails, everything depends on what happens next. A bad agent reports the error and stops. A good agent reads the error and adapts. It's that simple. This is what separates an agent that works half the time from one that works 90% of the time. Failure at agent scale isn't a dead end, it's data. The agent generates an implementation. A test fails. Instead of giving up, the agent analyzes the failure message to see exactly what went wrong. It looks at why the test broke and modifies the code to fix the actual problem, not just the symptom. Then it runs the test again. If it passes, great. If it fails differently, the agent analyzes the new error and tries a different approach. This is self-healing. The agent doesn't need you to intervene every time something breaks because it has the logic to fix itself. This capability matters more than you'd think. The research is clear. When agents can iterate, their success rate on complex tasks jumps dramatically. On SubWeBench Pro, agents with iteration built into their workflow achieve 70% success rates on difficult problems. Agents without that capability top out around 30 or 40%. That's not a marginal difference. That's the difference between a tool that's useful and one that isn't. The iteration loop is straightforward. The agent generates code. It runs the tests. If the tests pass, it moves on. If they fail, it analyzes the failure, modifies the code, and tries again. It keeps cycling until the tests pass, or it hits its iteration budget. That budget matters. The agent isn't allowed to iterate forever. Maybe it gets 10 iterations, maybe 20. After it exhausts that budget, it gives up and reports the problem to you. This prevents infinite loops and forces the agent to either make progress or escalate the issue. It keeps the agent from spinning endlessly on an unsolvable problem. The rubber duck protocol makes this iteration smarter. When the agent gets stuck after trying the same approach 5 times, it can call for help. It sends its plan and the current code to a reviewer. The reviewer is a different model family. It looks at the code with fresh eyes to spot the issue the primary agent couldn't see. It identifies the architectural misunderstanding or the edge case the agent overlooked. The reviewer sends back feedback, the agent reads it, and then it tries a completely different approach. It's not just retrying the same thing, it's pivoting based on new information. Importantly, the reviewer doesn't block the process. The agent doesn't stop everything and wait for feedback, so it can keep working while the reviewer is thinking. When the review comes back, the agent integrates it and adapts without losing momentum. Here's what makes this work at scale: logging and observability. Every iteration, every failure, and every adaptation gets logged. You can see what the agent did, why it failed, and how it fixed itself. This visibility is critical because it tells you where the agent is struggling. If it's iterating 10 times on one type of problem but only once on others, you know where to improve the context. Human feedback amplifies this. When the agent hits its budget and reports back to you, you see the full logs and understand the block. Maybe you see the agent was approaching the problem wrong, or you have domain knowledge that would have helped. You give feedback, and that feedback goes back into the agent's model. This isn't just for the current task, it's for future tasks. The agent learns. Failure isn't the end of the process. It's the beginning of the learning loop. But agents are only useful if they have the right tools to work with. Tool integration and the MCP protocol. The fundamental limitation of any agent is simple. It can only do what it has the ability to do. If the agent can only read and write files, it's constrained to those operations. The moment you give it access to more, the scope of what's possible expands entirely. You give it the ability to run tests, invoke APIs, check deployment status, and query logs. This is where the Model Context Protocol comes in. MCP is the standardized way agents get access to tools beyond just code. Here's the core problem MCP solves. Different tools work differently. Different APIs have different signatures and authentication requirements. Without a standard, every agent would need custom code to work with every tool. That doesn't scale. You'd spend more time writing integration code than improving the agent itself. MCP creates a common language. The agent doesn't need to understand the internals of every tool because it understands MCP. Tools implement the protocol, and the agent discovers what's available and how to invoke them. A tool might be a shell command to build the project or deploy to staging. It could be an API call to query the database or check metrics. It could be a documentation lookup to search the internal wiki and see how a module works. It could even be a file system operation that goes beyond basic reading. The agent can list a directory to understand the layout of a codebase without reading every single file. It reads the capabilities, understands the parameters, and uses the tools to validate its work. This is where the power actually lives. The agent doesn't just generate code in isolation. It runs tests against its own code and triggers a linter to see the actual style rules for your project. It can run security scans to find vulnerabilities or query the real database schema instead of guessing. It checks the logs to see what happens when the code runs. It can even deploy to a staging environment to validate that the change works in a real system. MCP is standardized, which means tools can be built by anybody. GitHub provides MCP servers for repository operations. Cloud providers provide servers for their services. Your organization can even write MCP servers for your own internal tools. Because the protocol is consistent, the agent can use any of them. A tool built by GitHub works alongside a tool built by Amazon and a tool built by your own engineers. GitHub's Copilot CLI uses MCP extensively. It accesses servers to search the repository, read documentation, and check workflow status. It invokes shell commands to run tests and validates its own work before asking you to review it. Other agents use MCP to access cloud provider tools. AWS provides servers for EC2 and RDS, while Azure provides servers for their own resources. The agent checks what resources exist and understands the current configuration. It proposes changes that actually work in that environment, not theoretical changes that might fail. The agent's capability ceiling is set by the tools available to it. If you only give it the ability to read and write code, that's all it does. If you give it access to tests, scanners, databases, and logs, it becomes much more powerful. This is why tool integration is not optional in the agentic stack. It's foundational. An agent without tools is limited to code generation. An agent with tools becomes an actual system agent. It understands the real state of the infrastructure and validates its changes against reality. This marks a structural shift. Agents are moving from read code and write code to understand the entire system. They trigger real actions that matter. That's the difference between a code assistant and an actual agent. The agent's decision-making process, reasoning and planning. How does an agent actually decide what to do? This isn't a rhetorical question, it's the reasoning problem, and it's exactly where most agent deployments fall apart. When an agent receives a task, you might tell it to refactor an authentication module to use OAuth2 and add full test coverage. Now the agent has a goal. But goals are not instructions. A goal is just the outcome you need. Instructions are the specific steps, do this, then do that, required to get there. The agent has to bridge that gap. It has to figure out the instructions from the goal. It has to break the task into steps, choose the right tools, and estimate if the approach will even work. All of this happens before it touches a single line of code. Planning is not trivial. It's incredibly difficult when you're operating across a real code base with dependencies, constraints, and existing patterns. The Agentic Stack uses several reasoning patterns to handle this, and each one has real trade-offs. The first is REACT, which stands for Reason, Act, and Observe. The agent reasons about what to do, takes an action, and then observes the result. Then it repeats. Reason, act, observe, reason, act, observe. This cycle continues until the task is done. The benefit here is flexibility. The agent can adapt as it learns. If something unexpected happens, the agent notices and adjusts its path. But the cost is speed. Every single cycle takes time. On a task that requires dozens of cycles, the whole process gets noticeably slower. Plan and execute is the second model. Here, the agent creates a complete plan before doing anything at all. It thinks through the entire sequence up front. It breaks the task into steps and decides which tools to use. It even tries to estimate where problems might occur. Then, and only then, it executes. The benefit is efficiency. The agent thinks once and acts once. There is no repeated reasoning on every minor step, but the cost is flexibility. If something unexpected happens, the plan might not account for it. The agent might hit a wall and be forced to stop and replan everything from scratch. Multi-agent collaboration is the third pattern. Instead of one agent doing everything, specialized agents handle different parts of the task. A planner agent creates the plan. An implementer agent writes the code. A reviewer agent checks the work. An orchestrator agent coordinates the whole group. The benefit is specialization. Each agent is optimized for its specific role. The code writing agent gets very good at writing code, and the review agent becomes an expert at finding bugs. But the cost is coordination overhead. More agents mean more communication. That creates more opportunities for miscommunication or conflicting decisions. The agentic stack we've been describing uses a combination of these. The orchestration layer, Copilot CLI, uses plan and execute for high-level decisions. You describe what you want, and the agent creates a plan. It shows you that plan. You approve it or give feedback. This happens once right at the start. It's efficient. But the implementation layer uses React. Once the plan exists, the agent executing that plan iterates. It writes code and runs tests. If those tests fail, it reasons about why. It modifies the code and runs the tests again. This iterative approach is what allows it to handle surprises. The quality of the agent's reasoning depends on three things: context, tools, and guardrails. An agent with poor context makes poor decisions. It reasons from incomplete information. It has blind spots. It doesn't understand the real constraints of your system. An agent without tools can only theorize. It can't validate its ideas. It can't check whether its reasoning is actually correct. It's just working from assumptions. An agent without guardrails either tries to work around constraints, which wastes time, or it ignores them entirely, which creates technical debt. But when an agent has good context, integrated tools, and clear guardrails, it can reason effectively. The context shapes how the agent thinks about the problem. The tools let it validate that thinking. The guardrails keep it focused on what is actually possible. This is the shift. The quality of the reasoning is not primarily about the model. It's not a case of smarter models reason better. In reality, better context, tools, and guardrails enable better reasoning. This matters because it changes how you build an agentic stack. You don't just pick the most capable model and hope for the best. You optimize the whole system. You engineer the context. You integrate the tools. You define the guardrails. The model matters, but the system matters more. Breaking deadlocks. When agents get stuck. An agent can reach a point where it is no longer making progress. It tries the same approach repeatedly. It hits the same failure again and again. It starts cycling through variations of an idea that fundamentally does not work. This is a deadlock. The agent is trapped in a state where forward momentum has stopped, and every new iteration produces the same broken result. The problem is that the agent doesn't know it's stuck. It thinks it's trying something different. It tells itself, I modified the code here. That failed. Now I'll modify it there. But the core approach is broken. The changes are just surface level. The fundamental problem hasn't been addressed. The agent needs a way to recognize this pattern and respond. Deadlock detection is the first part of the solution. The agent has to monitor itself. It watches how many times it has tried to solve the same problem. It checks whether the failures are actually different or just variations of the same error. If it sees the iteration count increasing while the success probability is decreasing, it recognizes a deadlock. When a deadlock is detected, recovery kicks in. The agent has a few options. The first is to invoke the rubber duck reviewer. As we've seen, this is where a different model family looks at the problem with fresh eyes. The agent shows the reviewer its current code and the failures it's hitting. The reviewer isn't blocked by the same assumptions. It might spot an architectural misunderstanding. It might identify a constraint the agent overlooked. It might simply point out that the entire approach is wrong. The agent reads this feedback and tries something completely different. Not a slight change, but a different idea entirely. The second recovery option is requesting human feedback. When the agent recognizes it's stuck, it can ask you directly. It might say, "I've been trying to implement this function, but tests keep failing. What am I missing?" You look at the logs. You understand the context in a way the agent struggles with. You provide feedback. You might say, "The issue is actually in how you're handling the validation step. Look at this other function in the codebase. It does this part differently." The agent reads that, incorporates it, and understands its blind spot. Then it tries again with a new direction. The third option is resetting and starting fresh. The agent can clear its working state and approach the problem from the beginning, but this time it carries the knowledge it gained from the previous failures. The fourth option is escalation. If the problem is simply beyond the current model's capability, the task can be handed off to a more capable model. Copilot CLI implements this deadlock recovery automatically. If the agent recognizes it's stuck, it can invoke the rubber duck reviewer without waiting for your permission. The review comes back, the agent incorporates the feedback, and it tries a new approach. All of this happens in the background. You just see that a deadlock was detected and resolved without you having to intervene. The research on this is very consistent. Agents with deadlock detection and recovery achieve significantly higher success rates than agents without it. This isn't just a small quality improvement, it's a structural difference. With deadlock recovery, agents can complete tasks that would otherwise be impossible. Without it, they hit walls and stay there. Logging is what makes this whole system work. Every attempt, every failure, and every recovery needs to be recorded. You can't understand why an agent is stuck without seeing what it's already tried. You can't provide effective feedback without the logs. And you certainly can't improve the system if you don't understand where the deadlocks are happening. The human is always part of the recovery process. Sometimes the agent recovers automatically through the rubber duck. Sometimes it needs your direct input. Either way, you are watching. You're learning what kinds of problems cause these loops. You're seeing where the context or the tools are insufficient. The structural insight here is simple. Deadlock is not a failure. It's just a signal that the agent needs help. The agent knows this. It doesn't panic. It just asks for what it needs. This is why the agentic stack includes multiple feedback mechanisms. The rubber duck provides one perspective. Human feedback provides another. Two results provide a third. Together, they create a system that can break free from almost any deadlock the agent encounters. Latency and time budgets, the performance constraint. There is a fundamental tension in building agentic systems that almost nobody talks about. Agents need time to think. Good reasoning takes time, deep analysis takes time, and iteration takes time. But the moment an agent takes more than a few seconds to respond, something inside the developer's brain shifts. They stop waiting. They stop believing the agent will deliver. They go back to doing it themselves. This is the latency problem. It isn't about whether the agent can do good work, but whether it can deliver that work fast enough that waiting feels rational instead of frustrating. The research on this is crystal clear. If the delay between asking for something and the agent starting its response exceeds a few seconds, usage drops. The agent might produce perfect output, but it doesn't matter because the developer has already moved on to the next thing. They've decided it's faster to just do it themselves. Copilot CLI has become fast enough that this stops being the limiting factor. Recent optimization updates claim up to 75% improvement in response time compared to earlier versions, and that number matters because it's the difference between an agent feeling like a tool you use and an agent feeling like a chore you endure. So how does this actually happen? Prompt caching is part of it. The agent doesn't resend the same context to the model on every request because that context gets cached. If you're asking the agent to work on the same project for a while, the repository structure, architecture, docs, and pattern files are all already in the model's attention space. The agent just talks to the model about what's changed since last time, which cuts the overhead dramatically. Streaming is another part. The agent doesn't wait until it's generated the complete response before showing anything to you. It streams the output as it's being generated, so you see words appearing, the plan forming, and actual progress. This changes your perception of speed. Even if the total time is the same, streaming makes it feel faster because you aren't staring at a blank screen waiting for something to happen. Context compression works at a different layer. The agent doesn't send your entire code base to the model, but instead analyzes what you're actually working on, what nearby code is relevant, and what patterns apply to this specific task. It bundles just that context and sends it. Full codebase context might be huge, but compressed context is tight, and the model processes it faster. Parallel execution runs multiple checks at the same time instead of sequentially. The agent doesn't finish reading the files, then plan, then start implementation. It can start planning while still reading, and it can start running tests while still generating code. Different parts of the workflow happen concurrently. But there's a hard limit to how fast you can make agents if you're trying to maintain quality. So the stack uses time budgets instead. The agent gets a budget where it can spend X seconds on planning, Y seconds on implementation, and Z seconds on validation. If it hits the budget, it stops. It reports what it's done so far and the developer reviews it. Either the developer approves and the partial work gets merged, or they give feedback and the agent continues with more budget on the next iteration. This matters because it changes what quality means. It's not, how good can this be, but how good can this be in the time available? The agent optimizes for that trade-off. It doesn't spend minutes on architectural analysis if the budget is 30 seconds, but instead makes quick decisions and moves forward. Different tasks get different budgets. A code review is tight because you need feedback on a PR now, not in 5 minutes. A simple refactor is tight, but a full feature implementation is looser. A major modernization task is loose because you aren't paying for the refactor to happen right now, but rather for it to happen eventually while you do other work. The structural insight here is that latency isn't just a performance problem, it's a design problem. Latency shapes how agents reason. Tight budgets force agents to be decisive, so they skip deep analysis and go for directional correctness. Loose budgets allow contemplation, so they iterate and refine. Understanding your latency profile is critical. You need to know how long different tasks actually take and where the bottlenecks are. Is it model inference that's slow? Is it tool invocation? Is it context preparation? Different bottlenecks have different solutions. Optimization is ongoing. As models get faster, as tools improve, and as your context preparation gets smarter, the entire stack gets faster. This isn't a one-time tuning, but a continuous process where you measure, identify slow paths, optimize them, and measure again. The point is simple. Speed matters less for quality and more for usability. Measuring agent effectiveness, metrics that matter. Here's the hard part about deploying an agentic stack. You can't tell if it's working just by looking at it. The agent generates code. The agent completes tasks. Everything looks productive. But is it actually moving the needle on what matters? This is where most organizations make a critical mistake. They measure the wrong things. They count PRs created, lines of code generated, and how many issues got closed. These are vanity metrics. The agent could produce 100 PRs, but if they're all garbage, you've just wasted time and energy. Real measurement is different. Real measurement focuses on business value, specifically 5 things. Throughput is the first. How many tasks can the agent complete per day? How many pull requests are being created per developer per week compared to before you deployed the agent? If throughput hasn't moved, the agent isn't actually working. Even if the agent is operating, it isn't saving anybody time. Throughput is objective, and either you're getting more done or you're not. Quality is the second. What's the defect rate in agent-generated code compared to human-generated code? What percentage of the agent's output gets reworked? How many bugs escape into production? This matters because a fast agent that generates garbage actually costs you money. The review burden increases, the rework burden increases, and you've accelerated something that doesn't work. Quality metrics tell you if the speed is actually real or if you're just moving faster in the wrong direction. Cycle time is the third. How long does it take from the moment a task is created to the moment code is merged and deployed? Not just how fast the agent works, but the entire cycle. Is your PR spending less time waiting for review? Are you deploying faster? Cycle time is the metric that actually connects to business outcomes. Faster deployment means faster feedback, which means you catch problems earlier, and your team gets information sooner about whether a feature is working. Developer satisfaction is the fourth. Do your developers actually find the agent helpful? Are they using it? Are they asking for more? This isn't a soft metric, but a signal about whether the system is actually solving a problem or creating new ones. If developers hate using the agent, they'll stop using it and all your investment evaporates. Satisfaction tells you if the interface is right, if the latency is acceptable, and if the outputs are useful in the context where they're being used. Technical debt is the fifth. Is the agent introducing new debt or reducing existing debt? Are the code bases it touches getting cleaner over time or messier? You can improve cycle time while introducing debt that costs you later. A good agentic stack improves cycle time while reducing debt, but a bad one does the opposite. Measuring debt means you're taking a long-term view instead of just celebrating short-term velocity. The research shows that when these 5 things are working together, the numbers are significant. Throughput increases by 30 to 100%. Quality improves with fewer defects and less rework. Cycle time drops by 20 to 40%. Developer satisfaction stays high and technical debt decreases. But here's what matters most. These improvements only happen when the agentic stack is actually well built, when context is rich, when guardrails are clear, when tools are integrated well. If you've cut corners, the metrics won't improve. You also need to measure what's happening inside the agent. Success rate tells you what percentage of tasks complete without human intervention. Iteration count tells you how many times the agent cycles before it succeeds. Tool usage tells you which integrations the agent is leaning on and which are sitting unused. Deadlock frequency tells you how often the agent gets stuck and needs help. These internal metrics are feedback signals. If the success rate is low, the agent probably needs better context understanding. If deadlock frequency is high, the tool integration is probably incomplete. If the iteration count is high, the initial planning is probably missing something. If certain tools are unused, they might not be discoverable or useful in the way you've presented them. The point, metrics aren't about accountability. They're about learning. They tell you where the agentic stack is succeeding and where it needs work. Continuous measurement matters. You aren't measuring once and declaring victory. You're measuring continuously, watching for trends, and identifying problems as they emerge. Continuous improvement, the feedback loop. The agentic stack isn't finished when you deploy it. That's when the real work actually starts. Every time the agent completes a task, something happens that matters. The work gets done, code gets written, and tests either pass or fail. When developers review those changes and use the output, they create a signal. This is vital information about what's working and what's broken. Most organizations ignore this signal because they deploy the agent and immediately move on. They're focused on utilization, not improvement, which is exactly why their agentic stacks plateau. They work okay for a while, then they just stop getting better. The teams that see dramatic gains treat the agentic stack like a product. It's a living thing that needs to grow. But here's the problem. Most people don't have a loop. In a real feedback loop, an agent completes a task and you capture the outcome. You look at whether it succeeded or failed. If it worked, you check how clean the implementation was and if it needed rework. If it failed, you ask why. Was it a context problem, a tool problem, or a misunderstanding of the requirements? You collect developer feedback too. You ask if the output was usable and if they would use it again. You analyze all of this to identify patterns across dozens of tasks. Then you make deliberate improvements. Context improvement happens first. If the agent repeatedly generates code that doesn't fit the architecture, your documentation is incomplete. You update architecture.md, you refine your gotchas, and you add pattern files for the specific problems the agent is hitting. You're encoding knowledge that the agent didn't have before. The next time a similar task comes in, the agent has that knowledge and the output improves. Tool improvements come next. If the agent is failing because it can't validate its work, you integrate the tools that let it validate. If certain tools aren't being used, they might not be discoverable or useful in their current form. You fix them or you remove them. You might even integrate new tools that solve the actual problems the agent is hitting in the wild. Guardrail adjustments are the third category. Based on the mistakes the agent makes, you refine the policy. If the agent violates architectural rules, you make those rules explicit in the guardrail files. If it's missing validation checks, you tighten the requirements. You aren't just restricting the agent, you're teaching it what good looks like. Prompt refinement is the final piece. How you ask for a task matters. If developers give vague tasks and the agent generates vague results, you create prompt templates. You show examples of well-specified tasks to the team. You refine how people ask the agent to do things, which changes what the agent understands about what you actually want. This isn't one-time tuning. This is continuous. Every week, you review the metrics from the prior 7 days to find the biggest bottleneck. It might be throughput, quality, or cycle time. You make one focused improvement and you measure the impact. Next week, you do it again. This cadence matters. Teams that improve continuously see measurable gains. In the first month, you might see 30% improvement as you fix obvious problems. The second month, gains might slow to 15%, and by the third month, you're looking at 10%. But the cumulative effect compounds. After 6 months, the agentic stack is 3 times better than when you started. The structural insight is this. The agentic stack is a learning system. It gets better as it operates. Every task that gets completed and every failure that occurs teaches it something new. This is why you can't treat the agentic stack as a deployment. You have to treat it as a product that needs ongoing management. You're measuring it, analyzing it, and documenting every decision you make. When new team members join, they need to understand the system. When something breaks, you need to know why you built it that way so you can debug it properly. Documentation is the glue that holds this together. It's not optional. It's how you preserve learning and onboard people into the feedback loop. It's how you maintain institutional knowledge about why your stack works the way it does. Organizational implications, shifting roles and responsibilities. When you deploy an agentic stack, you're not just changing tools, you're changing what people do all day, and that ripples through how the organization actually works. The most immediate shift is in the developer role. It stops being about writing code and starts being about defining intent and reviewing output. This isn't less work, it's different work. It requires a different set of capabilities. A developer using an agentic stack needs to be precise about intent. When you're writing the code yourself, vagueness doesn't matter much because you figure it out as you go. But when you're telling an agent what to do, vagueness is amplified. The agent takes your vague instruction and generates something that matches your words but misses what you actually wanted. Developers need to get better at articulating intent and thinking about the goal before they ask for help. They also need to get better at reviewing code they didn't write. When you write code, you understand every decision and you remember why you structured it that way. When the agent writes code, you're seeing it fresh. You need to read it critically and understand the architecture deeply enough to spot when the agent violated a rule. You have to trace through logic that someone else created. This is a learned skill, and not every developer starts out good at it. And decision-making becomes more central. Not every task the agent completes will be obviously correct. Sometimes the implementation is technically sound but doesn't match the business need. There are always trade-offs between speed and clarity or elegance and maintainability. Those decisions were always happening, but now they're more visible because the agent is surfacing options. Developers need to develop judgment about which choice is right. New roles emerge alongside this shift. The agent architect is one. This person designs how the agentic stack works and decides which agents exist and what guardrails contain them. This is an extension of the architect role, not a completely new position. Existing architects will start spending their time thinking about agent design. Context engineer is another. This is someone who maintains project memory and keeps architecture files current. They update the gotchas as new problems emerge and write pattern files that teach agents what good looks like. They manage the knowledge base that agents read from. This extends the senior engineer role, and some seniors will realize they're naturally good at encoding knowledge. Agent trainer is the third. This person monitors performance and watches which tasks succeed or fail. They collect feedback from developers and analyze logs to understand where the agent is struggling. They feed this insight back into improving the context and the tools. This is part of the architect role and part of the team lead role. The organizational structure doesn't have to blow up, but it often shifts. Instead of front-end and back-end teams, you might see platform and product teams. The platform team manages the agentic stack and keeps it running while the product team uses it. They focus on building features, not on the mechanics of code generation. Or you might see an automation team that specializes in agent workflows. They design how agents flow through your development process, and they own the orchestration layer. But here's what matters most. None of this works without trust. Developers need to trust that the agent is doing good work. This isn't blind trust, but informed trust based on seeing high-quality code over 1,000 tasks. That's the kind of trust that matters. Managers need to trust that agents are actually improving productivity, not just creating the illusion of activity. This trust is built on metrics like seeing cycle time decrease and throughput genuinely increase. This trust doesn't appear automatically. It's built through transparency. You show the metrics, you share examples of agent-generated code, and you walk people through the feedback loop. You demonstrate that the agent is learning and improving over time. The structural shift is fundamental. It's not humans do the work anymore. It's agents do routine work, humans do judgment. This isn't a small change. It affects hiring decisions, training, and how you evaluate performance. It changes career development, but it's also an opportunity. Humans get to focus on harder problems and features that require domain expertise. The boring, mechanical work gets automated. That's what every organization says they want. The ones that actually build agentic stacks that work will get it, while the ones that don't will keep doing routine work manually. Risks and failure modes, what can go wrong? The Agentic Developer Stack is powerful, but like any powerful system, it can fail catastrophically if you aren't careful about how you deploy it. These aren't hypothetical risks. They are real things that happen to teams that move too fast without thinking through the structural implications. The first failure mode is context collapse. The agent generates code that looks modern, but it's architecturally incompatible with your actual system. You wanted to refactor using new patterns, and the agent delivered those patterns, but they simply don't fit how your system is structured. Dependencies start flowing in weird directions. Cross-cutting concerns leak across boundaries. You end up with modern technical debt, which is just code written in a new framework but organized like an old messy one. This happens when context is poor. When the agent doesn't understand your architecture, it fills in the gaps with assumptions that don't match reality. Then there is quality degradation. The agent generates code that passes every single one of your tests, but it's fragile underneath. The tests check the happy path. They don't check if error handling is complete, or if performance holds up under a heavy load. You merge the code and it works for 2 weeks, until someone hits an edge case you didn't test for, and the whole thing breaks. This happens when guardrails are weak. It happens when validation checks aren't deep enough to catch subtle problems, or when you haven't defined what good actually looks like for your specific system. Deadlock is another major risk. The agent gets stuck trying to solve a problem and loops endlessly through variations of the same broken approach. It burns through your entire iteration budget without making any progress. At scale, this isn't just one agent stuck on one task, it's dozens of agents stuck on dozens of tasks. And your entire pipeline grinds to a halt while you wait for a resolution. This happens when tool integration is incomplete. The agent can't validate its own work, so it doesn't have enough signal to realize its approach isn't working. Over-reliance is more subtle, but it's just as dangerous. Your team stops thinking about the code. They stop reviewing carefully because the agent wrote it and the tests passed, so they just hit merge. This works fine until the agent makes an assumption you didn't catch, or the tests miss a critical edge case. The merged code becomes a massive liability. This happens when trust replaces judgment. People start treating agent output as finished work. instead of a first draft that still needs a human to look at it. The deepest failure mode is skill erosion. Junior developers never actually learn to code because the agent does the heavy lifting for them. They spend their time reviewing code instead of writing it. They make calls about whether generated code is good enough, but they never develop the muscle memory of building things from scratch. They never hit the walls that force you to develop real problem-solving instincts. A few years into their career, they can't function without the agent. They've become dependent on the tool, rather than capable with it. This is an organizational problem, not a technology problem, but it is very real. These risks exist, but they are manageable. The key is treating the agentic stack as a tool that augments humans, not one that replaces them. Humans make the final decisions. Humans review the code. Humans maintain the context. The agent doesn't take over those responsibilities. It just takes over the mechanical work. You also have to invest in the foundations. Building good context takes time. Strong guardrails require you to think through every possible failure. Tool integration is detailed, difficult work. And feedback loops have to be part of your daily process. Organizations that skip these foundations will fail. They deploy an agent, it generates garbage, they get burned, and then they abandon the technology entirely. But the organizations that invest in those foundations succeed. They deploy an agent and it generates useful code, they see real improvements, and they expand how they use it. The agentic stack becomes normal infrastructure, not just an experiment. The structural insight is this: the agentic stack amplifies what is already there. Good practices get better, bad practices get worse. If your code review process is weak, agents will expose that by generating code that slips right through. If your architecture is a mess, agents will amplify that by violating your rules in new and creative ways. You don't fix these problems with a better agent. You fix them by building the stack the right way, by investing in context, strengthening guardrails, and integrating your tools properly. This isn't a set-it-and-forget-it technology. It's an ongoing investment that requires constant attention. The teams that understand this will thrive, while the teams that try to deploy it passively will struggle. The terminal is no longer just for commands. It's the orchestration layer for your entire development workflow, the Agentic Developer Stack. With its layers for orchestration, transformation, validation, and execution, is how you build software now. It isn't about faster autocomplete. It's about agents managing the routine work, while humans manage the policy. Organizations that build this stack well will move faster, ship better code, and attract the best talent. Organizations that ignore this shift will simply get left behind. The question isn't whether you should use agents. The question is, how do you build an agentic stack that actually works? The answer is in the details. Context, guardrails, tools, feedback loops, and constant improvement.